Hello everyone. So, I welcome you all again to the third lecture of electromagnetic induction. I am Sameer Levankar. So, let us start with electromagnetic induction. As this is the third lecture, in the previous two lectures we have already covered introduction to electromagnetic induction, what is electromagnetic induction, what is the relation between current and magnetism, followed by experiments of Faraday and Henry. Just to recap, there were 3 experiments of Faraday and Henry, namely 1, 2 and 3. The first involved a coil denoted by C1 with a magnet M, either magnet moving towards the coil or magnet moving away from the coil, or magnet being stationary, coil going towards the magnet or away from the magnet. Experiment number 2 involved 2 coils, just replaced a bar magnet with a coil denoted by C1 and C2. Again the similar process of C2 going towards the coil C1 or away from coil C1, or C2 being stationary and C1 going towards coil C2 or away from coil C2. The third experiment also involved 2 coils, but this time one coil involved a tapping key. And hence in this was the difference between second and third experiment. Moving on to the third point, in the first 2 lectures I denoted something called as 0, something going to 0 to 5 units, then to 5 to 500 units, and I kept on talking about something called as units. When I talked about these units, I told to you that this is nothing but magnetic flux. So, this was magnetic flux concept being talked in the second lecture. Moving on to the Faraday's law of induction, the Faraday's law of induction was being told. Then Lenz's law and conservation of energy was being told. To reiterate what was Faraday's law of induction and Lenz's law, I will just go to previous slide. So, to just reiterate what was Faraday's law of induction. So, the Faraday's law of induction states that the magnitude of the induced EMF is nothing but voltage, also known as electromotive force. If the time persists, we will know what is electromotive force by today only. So, it is electromotive force, and the magnitude of the induced EMF in a circuit is equal to time rate of change. It is equal to time rate of change of magnetic flux, change of magnetic flux. Please be clear of this concept, it is change and it is not constant value, it is d phi b, and same rate of change of time, time rate. So, time rate is also dt through the circuit, and please make sure if anywhere circuit is written, that means it is an closed circuit. So, this was Faraday's laws of induction, and then moving on to Lenz's law, and similarly the Lenz's law states that the polarity of the induced EMF, polarity in mathematical terms is positive and negative value of the EMF is voltage here. So, the polarity of the induced EMF is such that it tends to produce a current is in I amperes, current I, which opposes the change in magnetic flux. Magnetic flux is nothing but phi b value that produced it. So, only the concept just says that if the deflection of galvanometer is towards, let us say right, then the current will be in anti-clockwise direction. Similarly, if the deflection of the galvanometer is towards left, then the direction of current in the circuit will be in clockwise direction. This is the only concept of Lenz's law. So, let us move on to our today's concept. So, after completing Lenz's law and conservation of energy, today we will be starting with a little discussion first on Lenz's law, and then we will move on to motional electromotive force and so on. So, this is the process we are involving. So, let us move on to today's work of discussion on Lenz's law. I need to talk about a little bit about Lenz's law more. So, let us move on to discussion on Lenz's law. A little small discussion is required here to understand the concept more. So, as you can see, there is a figure here on the right. The blue portion is the magnetic field here, and from these dots, from these cross values, it can be understood that the direction of the magnetic field is inside the screen. If you are seeing it on a screen, and it is inside the screen. If you are seeing it on a laptop, it is away from you, it is going away from you. So, cross sign depicts that it is going away, and dot sign means it is towards. So, let me first line by line explain the things written on the left hand side, and then we will discuss more. So, figure shows planar loop. So, as it is a planar loop, it is a simple plane, that is why it is known as planar. So, figure shows planar loops of different shapes, either it can be a square, a rectangle, a triangle, or any uniform shape also. Anything which is planar, that is of 2D shape, is called as a planar loop. So, figure shows planar loops of different shapes moving out of or into a region. As you can see, it is going out of the region, it is going inside the region, it is going out of the region, into a region of magnetic field. This was magnetic field, as I already told you, which is directed normal to the plane of the loop. It is directed normal to the plane of the loop because the plane is the, if I show you like this, then this is the plane here and you are going inside. So, as it is normal, it is perpendicular, hence it is written that it is directed normal to the plane. It is directed normal to the plane of the loop away from the reader. As I already told you, it is away from the reader. So, only that line has been iterated here. Let us move on to next line. So, it was a question, it is a simple question, I need to discuss about it, that determine the direction of induced current in each loop using Lenz's law. Direction as in it is moving in clockwise direction or anti-clockwise direction, only this is being asked. So, the first please now focus on this first point here. The magnetic flux to the rectangular loop ABCD increases due to the motion of the loop into the region of magnetic field, as it is clearly visible that as this ABCD portion will go inside, it will be something like this. It will be A portion, this will be your B, this will be your C, and this will be your D. So, it is quite evident, it is quite clear that the magnetic field inside that ABCD or inside that area is increasing. So, first it was only been acted in this area. The area was, as the area was small, that is why the magnetic flux going through that area, going through that portion will be small. As the area is increased, as you can see from this formula also, as the area will increase, so magnetic flux will also increase. So, next time what happened was, the complete area was under magnetic field. So, as the area got increased, so magnetic flux got increased. So, this is the only concept which is told in the first line here. So, moving on, the induced current must flow along the path BCDAB. So, what is the path BCDAB? BCDAB, that means it will go in anti-clockwise direction, because the magnetic field is increasing. As the magnetic field is increasing, it will counter it. How to counter it? It will go in anti-clockwise direction. So, this is the concept being told about here, so that it opposes the increasing flux. So, if there is an increasing flux, I will write here again, so that everything is being talked about. So, if the flux is increasing, so in this case it will be an anti-clockwise direction of current also. Let me write current also. And if it is decreasing, if the flux is decreasing, then it will be a clockwise, let me write direction also. I will try to be more clearer, clockwise direction of current. Okay. Let us move on to next point. So, next point says that this is done. Due to the outward motion, magnetic flux through the triangular loop ABC. Now, we are talking about this portion here. So, due to the outward motion, the magnetic flux through the triangular loop ABC decreases. As you can see, first of all, let me again use a different color for more clarity. So, first, in the first scenario, this complete area was under magnetic field, and after some time t, the area which will be under its influence will be nothing, no area is approximately 0 or 0 if it is very far from the magnetic field, yes, if it is very far from the magnetic field, that means that the magnetic flux inside the area has been decreased, that is phi b has decreased. So, due to the outward motion, the magnetic flux to the triangular loop ABC decreases please make sure it is decreases, due to which induced current is along BACB. So, what is the path BACB? If you see, BACB is a clockwise direction, as I already wrote here. So, these are only the 2 points which are being discussed simultaneously in this discussion. Moving on to the third point here then, as the magnetic flux decreases due to the motion of the irregular shaped loop ABCD. So, irregular shaped loop, again I will use 2 colors to make it more clearer. So, in the first scenario, this is the area we are talking about. This is the area which is under the influence of magnetic field. After some time t, I will try to make similar diagram. So, after some time t, area is almost 0, or if we are very nearer to this portion, then a little bit part can be under the influence, but the overall concept is that the phi b value will decrease. So, again I will read the point. So, third point says that as the magnetic flux decreases due to the motion of the irregular shaped loop ABCD out of the region of magnetic field, the induced current is along CDABC. So, CDABC, that means it is also clockwise direction, similar to the point I wrote here, to oppose the change in flux. So, after reading these 3 points, 2 concepts are being involved here. First I will clear everything and then I will explain those 2 things again. So, the first concept involved was if there is an increase in the area, as in if there is an increase in the magnetic flux involved with any planar shape, then there will be an anti-clockwise direction of current. So, this is the first concept being talked. The part of that concept is if the thing is reversed, that is if there is a decrease in the area. If there is a decrease in area, that will tend to decrease in the magnetic flux. If there is a decrease in the magnetic flux, then there will be a clockwise direction of current. So, this is the first concept being talked about, and the second concept is that it does not matter that the planar shape is a regular shape or an irregular shape, because see, it is a regular shape, but this is not a regular shape. This is not regular shape. That means it does not matter for this concept to hold as a function, or it is not dependent that the planar shape should be a regular shape or an irregular shape. So, these 2 things I needed to discuss, and hence this example was being used. So, to conclude it, note that there are no induced current as long as the loops are completely inside or outside the region of the magnetic field. What does this thing say is, I will explain it with an example. Let us suppose this is a rectangle which is capital A, capital B, capital C and capital D. If I move it in this direction and this is its new position, if this is its new position, capital A dash, B dash, C dash and D dash, then from moving from this position 1 to this position 2, the change in magnetic flux was 0. As there was a change in magnetic flux was 0, hence the induced EMF is 0, because induced EMF is nothing but a function of d phi. If d phi is 0, then induced EMF will be 0. So, this is the only concept being talked here, and similarly if it is outside also, then also as the magnetic field is 0, as B is 0 in both positions, therefore d phi is 0. If d phi is 0, then also similar case will occur. So, this was the discussion I need to talk about in this concept. So, let us move on. Now, let us move to the next concept, that is motional electromotive force. What is this motional electromotive force? I will explain it clearly to you. First of all, I will try to explain what is the figure here. So, in this figure, please try to recollect everything. So, it is a rectangle shaped thing. You can see something called as V here. So, it is something like this PQ bar is being moved here. You just try to understand it roughly, then you will I will keep on explaining every point, then you will understand what is happening here. And this crosses, as I already told you, are magnetic fields. Because it is a cross means it is going away from us. So, if you are watching it on a laptop, then it is going away from you, it is going inside the screen, and if it is a dot, then it is coming towards you. Okay. So, this is only the thing, there is nothing new in this concept here. So, I will go forward. So, let me explain you line by line. So, first of all, let us consider a straight conductor moving in a uniform and time independent magnetic field. What does these 2 points mean? So, first point means that the value of B is constant, the value of B is constant, value of B is constant, it is not varying with space or time. What is time independent? Time independent again means that it is a magnetic field. At time t is equal to 0, it was B. At time t is equal to any time t, it was B. So, these two things are this concept involved here. So, figure shows a rectangular conductor PQRS in which conductor PQ is free to move. So, this is the conductor PQ and this is free to move. This was the first point. Moving on. The rod PQ is moved towards the left with a constant velocity V. Please make sure that it is constant velocity, it does not vary, because if it is vary then the concept might differ. For now we are going to for simple terms and it is a constant velocity V. So, the rod PQ is moved towards left, the rod PQ is moved towards left with a constant velocity V as shown in the figure. Assume that there is no loss of energy due to friction. So, it is just a simple assumption, because if the energy is lost, then the concept or the formula which we will get in the subsequent slides which will be not accurate enough. That is why we are assuming, this is an assumption, that there is no loss of energy due to friction. Why there will be a friction? Because of the movement of the conductor PQ inside the magnetic field. So, PQRS forms a closed circuit, PQRS forms a closed circuit enclosing an area that changes as PQ moves. So, it is quite evident that if this conductor is at the position which it is already shown in the figure, then if the area is A1 and it goes inside, let us say here, let the new position be denoted as P dash and Q dash, and the area denoted by it is A2, then it is quite clear that A2 is less than A1. So, this is only the point wrote here. Next is, it is placed in a uniform magnetic field B, magnetic field is denoted by B value, which is perpendicular to the plane of the system. As I already told you, it is perpendicular to the plane of the system. We are talking on the plane, you can assume it that the laptop or your laptop screen is a plane, and anything which is going inside is the magnetic field B, which is perpendicular to the system. So, now if the length RQ is x, it is already given to you, if the length RQ is x here, and RS is L, and this is L here, already denoted, then the magnetic flux phi B enclosed by the loop PQRS will be phi B is equal to BLX. Why is it BLX? So, at this instant phi B is nothing but B dot A, dot, it is a dot vector product. So, it is B into A into cos theta. As the direction of magnetic field B is going inside the screen, and as this is a planar loop and the direction of the planar loop area A is also towards the screen, is also away, going inside the screen. So, the value of theta will be 0. As theta is 0, that implies that cos theta will be 0, cos 0 will be 1, that gives you B into A, B is already B and A will be L into x. So, that why this is the concept here. You should understand that where should be the direction of A, because sometimes the direction of cos can be 180 also, and sometimes the value of cos can be 0 also, and in both these cases the direction or the polarity may differ. So, that is why please understand the concept carefully, that where is the direction of the area vector going, where is the direction of B value, that is magnetic field going, because that will change the induced EMF also. That is why it is very important to understand. So, please understand every concept here very carefully. So, moving on to the next slide. So, just to reiterate again, so this is the value of phi B initial. Now, since x is changing with time, quite evident that as the PQ conductor is going inside, so the x value will keep on decreasing, it will keep on decreasing. Since x is changing with time, the rate of change of flux phi B will induce an EMF given by, So, as we already know, according to Faraday's laws of induction, that phi is nothing but minus d phi by d phi b by dt, also written here for your quick reference. So, epsilon is equal to minus n d phi b by dt, n is the number of coils. If number of coils are increased, then the induced EMF will be increased n times. So, epsilon is equal to minus n d phi b by dt, which is equal to minus of phi b written in the previous slide. So, what we got phi b as is BLX, we are just using it in the next equation. So, it is minus of d phi d BLX by dt, as B and L are constant and x is only a function of, as x is a function of time and B and L are constant. Hence, B and L goes outside the differentiation, and therefore, epsilon is equal to minus BL dx by dt. And from the simple mechanics formulas, we know that dx by dt is nothing but the velocity. Therefore, we have where we have used dx by dt is equal to minus v, which is the speed of the conductor PQ. Please make sure that here dx by dt is minus v. Why is it minus v? Because x is a decreasing function, x is decreasing. Because x is decreasing, that is why we have put the sign of negative here. Moving on, the induced EMF BLV is called motional EMF. So, this is also epsilon only, but because it is due to a movement, this is due to a motion, that is why the physicist or whoever made this concept, they told this as motional EMF. So, this concept is nothing but motional EMF. Moving on, we are able to produce induced EMF by moving a conductor instead of varying the magnetic field. So, this time B was not being varied, B is not varied, B was not varied, B was kept constant. This time A was varied, and due to a change in A, there was a change in magnetic flux, and as there was a change in magnetic flux, there was a induced EMF. So, I will iterate this point again. So, we are able to produce an induced EMF by moving a conductor instead of varying the magnetic field, that is by changing the magnetic flux enclosed by the circuit. Please make sure that here circuit is closed. So, the next concept now, after we have already found out what is the induced EMF, what is the induced voltage, let us find out the work done. So, the work done in moving the charge from P to Q is W is equal to Q into V into B into L. Since EMF is the work done per unit charge, E is equal to W by Q. So, here E is nothing but epsilon value. So, epsilon is nothing but work done per unit charge. So, epsilon is equal to W by Q, and in the previous concept here, from this equation, we also know that EMF is B into L into V. Therefore, from this equation we got that W is equal to Q B L V. So, this equation gives EMF induced across the rod PQ and is identical to the above equation. So, this is just basic of how the work done by a charge is being calculated. So, thank you.